Okay, let's take a look at our first stoichiometry problem. And before we do that, we're asked to balance um, the equation for the combustion of octane. So again, remember that a combustion reaction uses O2 as the fuel to burn, in this case the octane, to produce carbon dioxide and liquid water. Obviously, a very important problem for the combustion of automobiles. First things first, we won't balance the oxygen first. We're going to pick an element that appears only once on both sides. So here we started with carbon. So I put an 8 in front of the carbon dioxide, a 9 to balance out the hydrogens on both sides. And we acknowledge that there are 25 oxygen atoms on the right, but only 2 on the left. So at this point, you should immediately see what we need to do, and that's to use a fractional coefficient to gain access to 25 oxygen atoms on the left. Again, we want whole numbers, so we're going to multiply by 2 to get our final answer like so. All right, let's think about what this balanced equation means before we move on to our stoichiometry problem. This means that in the combustion of octane, for every 2 molecules of octane that are combusted, we need 25 molecules of O2. It's going to produce 16 molecules of carbon dioxide and 18 molecules of water. The same thing holds true for moles, and that's going to be the very key thing for our stoichiometry problem. For every 2 moles of octane that react, we need 25 moles of O2, and it's going to produce 16 moles of carbon dioxide and 18 moles of water. So armed with that, let's move on to the next problem, where we're asked how many grams of O2 are consumed during the combustion of octane. And we're going to use these numbers as conversion factors between the moles of reagents and other reagents, or reagents and products, or products and products. It doesn't matter which compounds we go between, as long as we use the numbers in the balanced equation. So we're starting with octane, which is C8H18. And it's important to remember that this dimensional analysis problem is actually more or less the same to all the other ones that we've done before. The only thing that's new is now we're going to convert between moles of one reactant and, in this case, moles of another reactant using the balanced equation. But other than that, this should look very familiar. We've done this conversion before, of course, and we've gone from grams to moles, of course. So as we map out our basic strategy using dimensional analysis, it should be very familiar to the ones that we've used in the previous sections. Grams go on the bottom to convert from grams of octane to moles of octane. And this is the key stoichiometric step here. Notice I actually write out the formula. This really helps me, and I still do it in my own work. It helps me figure out which numbers go in the numerator and the denominator. If I omit octane and omit O2, I might not know which moles I'm talking about. So I always write out the formula here. I find that it's easier for me to grade as well. So moles of octane in the denominator, what that's going to mean is that a 2 goes here and a 25 goes in the numerator. So keep that in mind as you're doing your own stoichiometry problems. It's really going to help you avoid mistakes and save you some partial credit. So let's plug in the conversion factors in the numerical values. We know that the molar mass of octane is 114 grams per mole. The balanced equation tells us that the 25 goes in the numerator. For every 25 moles of O2 that reacts, we need 2 moles of octane. And the molar mass of oxygen gas is, of course, 32. So when we do this out, we get 7.018 grams. Significant figures are not right. We started with 3, so let's keep 3. And let's also think about what this answer means. This means for every 2 grams of octane we burn, we need 7.02 grams of oxygen for the combustion reaction. And this is really important because it tells chemists what values they need to think about when they're designing and what amounts they need to think about when they're designing reactions. So this is our first stoichiometry problem. Good luck.